realize is that what and what you need to extract what and what they have in common. Okay. You need to extract what and what they have in common. We are told that they are all made of steel. So if they are all made of steel, then their densities must be the same. Of A and B must be the same. They are all subjected to the same tension. So tension of A and B, same. So these are same stuffs. Okay. But one thing you must also understand is that the first overtone of A is equal to the second overtone of B. So what is the first overtone of A? And what is the second overtone of B? The first overtone is equal to the second harmonic by our knowledge. Second harmonic. Whereas the second overtone is equal to the third harmonic. And second harmonic in strength is 2 times the fundamental notes. Third harmonic is 3 times the fundamental notes. So all that they are saying is that 2F1, which is the first overtone or second harmonic of A, is equal to the second overtone or the third harmonic of B. And we are also informed that the radius, if the radius of A is twice that of B, so R of A is equal to 2 times radius of B. These are the keynotes you must, be able to extract to help solve the question. Okay. Now, F1 is given by 1 over 2L times T on mu. Here, we are not informed of same length or 1 meter length, blah, blah, blah. So we are using mu. So mu, as we know, is equal to M over L. Since there is a talk of radius and then densities, we must express mass in terms of density and radius. Mass is equal to density times volume. And volume is equal to cross-sectional area pi r squared times the length of the string divided by L. So you realize that these 2 L's will cancel out and we'll have the linear density being equal to rho pi r squared. Okay, therefore, F1 will be equal to 1 over 2L times T on rho pi r squared. If you have any question here, you can quickly ask. Is there any question? Emma, do you have any question to ask?
Yes, please. No, please, sorry, I have nothing.
Okay. All right. So F1, the first overtone is equal to the second overtone of B. So 2 times, this is F1. So I'm substituting. Okay. 2 times 1 over 2LA. I'm doing it for this. Okay. Times T on mu now is this. So rho by R of A squared must be equal to 3 times F1, 1 of 2L of B times T on rho pi R of B squared. Fine. All right, Rachel, I'll do that. I know we have this. We have this. That R, the radius of A is 2 times the radius of I know. But I'm going to maintain them till, okay, the final state. So this is where I've reached now is this, after substituting F1 for A and B. So this and this cancels out. Then we'll have 1 over L of A. Okay. Then I'm coming. Now over here, this is R squared. And when you square R, when you square, take the square root of R squared, we'll have RA here multiplying this. So times T on rho of pi is equal to 3 on 2 LB R square root of R squared. So it will also come out R of B out times T on rho pi. This and this will cancel out because they are the same. Don't forget, this is density of A, density of B. But because they are all made of the same material, steel, their densities are the same. The reason for which I'm not distinguishing A from B. Okay. So this is what we have. We have 1 on LA RA is equal to 3 on 2 LB RB. Then in the question, we're told that R of A is equal to 2 times R of B. So I substitute this for A. 1 on LA times 2 RB is equal to 3 on 2 LB RB. RB will cancel out. And if I want to have a ratio of that. Where are we? There is something wrong somewhere. Okay, from this stage, let's substitute the value of this. Let's substitute R of A equal to 2 RB into the equation. Okay, I think what is wrong is at this stage. So let's clear this stage and then substitute whatever we're given for RA. We are told that RA is equal to 2 times that. So let's substitute that 1 on LA times T on rho pi. RA is equal to 2 RB squared is equal to 3 on 2 LB T rho pi RB squared. And when we do that, we'll have T on 4 rho pi RB squared over here. So we'll have the 2. Yes. Then 3 on 2 LB T rho pi RB squared. Then when we square 4, we have 1 on 2 LA T rho pi RB squared, meaning we've taken the square root of this 4 and it will be 2 is equal to 3 on 2 LB T rho pi RB squared. Then this side will cancel out. Okay, this side will cancel out, so that we'll eventually have 1 over 2 LA is equal to 3 on 2 LB. Okay, so that if we want LB on LA, we send LB to this side. We'll have LB over LA being equal to 2 would also multiply the 6 on 2. And 6 on 2 is equal to 3 on 1. So the ratio of LB on LA will be equal to 3:1 or 1:3. Amma, have you noticed where you went wrong?
Yes, please.
Okay, let's go through it for the last time so that those who just joined us can also follow. So let's clear everything. Let's clear everything. So the question says that 2 uniform strings A and B yes, I get you. You get the same answer. So just go through it. Well, what matters is your understanding, okay? 2 uniform strings A and B made of steel are made to vibrate under the same tension. If the first overtone of A is equal to the second overtone of B. So things you must understand: 1, the first overtone, and then the second overtone. The question says that the first overtone A, first overtone of A is equal to the second overtone.
Yeah, yeah,
Herbert, please mute yourself. Herbert,
yes, sir.
mute yourself for us. And what is the first overtone?
You.
The first overtone is the second harmonic. Second harmonic. In strings, the harmonics are odd and even. So this is equal to 2 times F1. The second overtone is also equal to the third harmonic. The third harmonic, which is equal to 3 times F1. So basically, all that they are saying is that 2 times F1 of A is equal to 3 times F1 of B. And what is F1? F1 is equal to 1 over 2L times T on mu. Okay, now let's simplify this. Since we have changing mass and length, let's simplify to get an expression for mu. Mu is M on L. The question talked about density. Same material, steel. Okay, and then different length. And it talked about radius. So we'll express the mass of the string in terms of density and area. So this is density times area is pi r squared. Pi r squared. So density times volume, but B is equal to area times the length. So pi r squared L divided by L, so that the length will cancel. Okay, and eventually we have the linear density to be density times pi r squared. So F1 would be equal to 1 over 2L times T on pi rho r squared. That is how the harmonic will be changed to. So if I want F1 of A, F1 of A will be equal to 1 over 2LA, length of A, times, you see, I can even ignore all the constants. Here, since T is the same, pi is the same, rho is the same, I can even eliminate this and say that then F will be inversely proportional to 1 over the length, okay, times R. Because when I take the square root of R squared, I'll get this. Okay, but you are learners, so after you have well understood it, you can take your own time to go through this yourself, where you eliminate the constant and then have it as this, and you get the same answer. So let's go through everything and then see where those things that can be cancelled will do so. So F1 of A will be equal to 1 over 2 L of A T on rho pi R of A squared. Here I'm not distinguishing the density because they are the same. Tension is the same. Pi, of course, is a constant. Okay. Meaning that F1 of B would also be equal to 1 over 2L of B T pi rho R of B squared. Then I'm told that R of A is equal to 2 times R of B. Okay, so I'm going to substitute that as well. So 1 over 2 L of A T on rho pi. This is R of A squared. So 2 times R of B squared, which will give us 1 on 2 LA T on 4 pi rho r of b squared. Okay. Now, this is the first harmonic is 2 times f1 of a. So I have f1 of a, I have f1 of b. I'm going to now substitute. So I have 2 times 1 over 2 LA. Now this is 4. When you take, this is 1 on 4. When you take the square root of that, it's equal to half. So this is 1 on 2. Okay. Then RB squared would also be times 1 on RB. So that we'll be left with T pi rho. Okay. This will be eliminated. Then we equate it to 3 times F1 of B. And this is F1 of B. 3 times 1 on 2 LB hold on, F1 Y, okay, I've seen it. 3 times 1 on 2 LB times 1 on RB, when I take the square root of this, times T on pi times rho. So straight away, you realize that this side and this side will cancel out. These two sides will cancel out. Okay. Then RB here, when you cross multiply, they will also cancel out. What do we then have? We have 1 on 2 LA is equal to 3 on 2 LB. Then you take your ratio. Okay, either LB on LA or the other way around. So if LB over LA is what you so desire, then you have 2 multiplying the 6 divided by 2. And 6 divided by 2 is 3 on 1. So the ratio is 3:1. Okay. So it's not so difficult, but you need to take your time gradually to go through it and then apply the concept, and it will be fine. Is there any question? All right, then let's quickly move to the second question. I know sometimes the questions may be tough, yes, because of the level of thinking which must go into it. But when you are given such challenges, please just do your best to try and then sit on it, because when you are trained with things like that, eventually you realize that WASSCE questions or around the same topics will be easier. Students actually testify to that training. So do not be so worried that Mr. Bia's question sometimes, okay, it's a deliberate way of training you. I've had situations where after students writing WASSCE, but said, WASSCE is like this and your questions is yes. You need to be trained tough so that when you meet less tougher opposition, you can easily overcome. So when I give it to you, please do not be so much alarmed. Spend time to try it, okay? All right, the tension of a stretched string is increased by 69%. Okay, the tension increased by 69%. In order to keep its frequency of vibration constant, its length must be increased by what? Okay, so the same spring, okay, it's the tension within is changed by this amount. Now, in order to have equal frequencies, how should the length change? So here the constant has to be the frequency and then the mass per unit length. We are changing the tension in order to change the length. Okay. Now we know F to relate to 1 on 2L T on mu. This is constant. F is constant. So if you pick F1, F1 must be inversely proportional to, the tension, must also be inversely proportional to the length. This is because this and this, the mu is constant. Okay, so when you vary the length, F2 must be proportional to T2 and inversely proportional to L2. But in order to have the same length, meaning that if you take a ratio of this and this, F1 on F2 is equal to root of T on L1. Let me indicate this, L1, L2. Okay, over L2 on root of T2. All right. Now we are told that in order to have the same length, so what we can do is that we can quickly equate root of T on L1 to root of T2 on L2 in order to have the same frequency of vibration. Okay. Now, we are looking for when the tension is changed to, hold on, this is T1. When the tension is increased by 69%, okay, so we have T1 on L1, then the tension is increased by 69%, and this is 169 of T1. The new tension is increased by 69% of the original. So 169 of T1. Okay. Now what will be T2? T2 is also, now what is L2? We are looking for L2. Now in terms of percentage, we realize that, okay, let's equate L2 on L1. L2 on L1 is equal to 169 T1 of T1. And T1 will cancel out. Therefore, L2 will be L1 times square root of 169. And what is the square root of 169? What is the square root of 169?
13.
I'm coming. This must be 100 of T1 because initially T1 was 100% and it was increased by 69. So it must be T2 must be 169 of T1 and T1 must be 100%. Okay. So when we take that, we have 169 divided by 100, and this must give us, I think, 1.3. 1.3. When we take the square root of this must be equal to 1.3. So it means that if you increase the tension by 69%, L2 will be equal to 1.3 of L1. And what is 1.3? 1.3 is 130% of L1. Meaning that when you increase tension by 69%, the length must also be would increase by 30%. So the change in length must be 30%, so that they are in order to have the same frequency of vibration. So if you increase tension by 69%, the length would also be increased by 30%, so that they can have the same frequency of vibration. Okay. Then the last question. The last question. A tube closed at one end. Let me flip the camera. A tube closed at one end and containing air is excited. A tube closed at one end and containing air is excited. It produces the fundamental note of 512. So a tube closed at one end, which is this, produces a fundamental note of 512 Hz. What is this note? The note will look like this. If the same tube is open at both ends, the same tube, meaning the same length, this time open at both ends, if the same tube is open at both ends, what will be the fundamental frequency that can be produced? Okay, so we don't know the fundamental frequency if the same tube is open at both ends. But this L length is equal to quarter lambda. So F1 here will be equal to V on 4L. This same length, L length, is equal to half of lambda. Okay, and so F1 here would also be equal to V on 2L. Okay, now when we look at what we have, the common factor has to be the length. The lengths are the same. So if we make L the subject from this, we'll have L is equal to V on 4F1. Okay, when we make L the subject, V on 4F1. When we make L the subject here, we'll also have V on 2F1. Because they are the same, we can now equate the lengths. Because L here are the same. So V on 4F1 is equal to V on 2F1. V is the same velocity of sound in air. Okay, so we are looking for this F1 is given for close F1 for closed pipe. Closed pipe at one end is given. The open pipe we do not know, and the open pipe F is this one. So this is for open. This is for closed. So we make the open the subject. Okay. F open will be equal to velocity of sound in both situations the same. So we can cancel that out. So we have 1 on 4FC is equal to 1 on 2FO. When we make FO the subject, we have FO is equal to, FO will be equal to 4F of C divided by 2. This is equal to 2FC. And FC, we were told, is 512. So 2 times 512, which will give us 1,024. 1,024. So F when close to be 1,024 hertz. So please, when the question is given, take your time and apply whatever concept you've learned, and look out for the common factors. What are common in them, and then identify the difference. Okay, here you must distinguish the fundamental frequency for closed from the fundamental frequency when it is opened, and it's really simple. Please, is there any question? Is there any question? Okay, let's continue from where we ended. We went through open and closed pipes last time. Now there is another consideration to that, to the open and then closed fundamentals. In open pipes, in closed pipe, we saw that the frequencies are odd. So for closed pipe or tube, we got the frequencies to be odd harmonics. We had odd harmonics. F1, the next 3F1, 5F1, to 2N minus 1 F1. These are the harmonics. Okay, and the coefficient 1 is to 3.
Let me tell you what happened to me. This is physics thing. You've learned it already. So, yeah.
Nathaniel. So the harmonics 1 is to 3, is to 5, is to 7, on and on and on. And then for open pipes, okay, we got the harmonics as both even and odd. 1 F1, 2 F1, 3 F1, 4 F1, on and on. And the end harmonic, we got NF1. So the coefficient, we have 1 is to 2, is to 3, is to 4, on and on and on. These are odd. These are even and odd. Even and odd. Okay. Now, let's consider an end correction. what we mean by end correction. You see, if you blow air into tubes, you realize that as you blow the air, you feel the air, okay, around your mouth as well. As you blow, you feel the air around your mouth. Reflection of the air which is blown into the tube. Okay. The air blown within is what creates the stationary wave. But you realize that the air or the stationary wave created does not exactly fit the length of the tube. But so it goes beyond the length of the tube. The reason for which you feel, okay, you feel a reflection of the air blown into around your mouth. Okay, so that the extension of the stationary wave or of the notes within the tube, okay, beyond the barrier or the pipe or the tube is what we are calling as the end correction. Earlier, we considered when we have for open, when we have the tube fitting directly into, or the stationary wave fitting directly into the tube. When we consider an end correction, the same tube, we realize that the stationary wave goes beyond the length of the tube or pipe a little. So there is an overlap. This little extension beyond the length of the pipe or tube, this is the length of the tube, L. But the stationary wave formed can go beyond or can extend beyond the end of the tube. That little difference is what we are calling as end correction. Okay. So the end correction is the extension of the notes or of the stationary wave beyond the length of the tube. Extension of the notes or the stationary wave beyond the end of the tube or pipe. There are times that can be considered. There are times that can be overlooked. Okay. So if it is not considered, it will be drawn as this. If it will be considered, it must be drawn as this. Okay. Now, if you have a closed pipe, a pipe closed at one end, there is formation of end correction at the open end. So for closed pipes, an end correction is formed at the open end. If you have an open pipe, a pipe open at both ends, there is formation of end correction at both ends. So the note goes beyond it at both ends. So there will be an end correction here. There will also be an end correction here. So for open pipes, pipe open at both ends, you have two end corrections because both ends are open. For a closed pipe, only one end experiences, only the open end experiences an end correction. Please, is that understood? Hello?
Yes, please.
Now, if there is an end correction, let's look at how that can be factored into the notes, the harmonics. Let's see how end correction will be factored into the frequencies or the harmonics for both closed and open pipe. So for this note, which is open at one end, we saw the harmonics because L will be equal to quarter lambda, and lambda is equal to 4L. We saw the fundamental to be equal to V on 4L. If there is a consideration for end correction, this is how the harmonics will change. So there is, Charlotte, are you there?
Yes, please.
Draw it well.
I will.
Add aesthetics to your drawing. So here we are considering for that little extension. So we realize that this is the length of the tube. In this case, it is not L, which will be equal to quarter plus E. No, this is wrong. This is because the note within is longer than the length. So it is rather the wavelength, which is quarter lambda, that must be equal to L plus E. Okay, because the stationary wave goes beyond the length of the tube. So it must, the stationary wave within must be equal to the length of the tube plus the end correction. Okay, so in this case, lambda will be equal to 4L plus E. And if lambda is equal to 4L plus E, then the harmonics, the frequency, fundamental frequency, will be equal to V on 4L plus E. So that is how to factor into the equation when there is an end correction for a tube closed at one end. Let's look at how it will change the harmonics for when we have a tube open at both ends. So for a tube open at both ends, without end correction, we have this. So here the length of the tube is equal to half lambda. Therefore, lambda is equal to 2L, and the fundamental frequency becomes V on 2L. If there is a consideration for end correction, denotes there's extension there's that little extension here and there. So we have E and correction E over here, and then N correction E, meaning the length of the tube is actually from here to here. So the note, which is actually half lambda, is equal to L plus 2E. This length plus 1E here, 1E here. Therefore, lambda will be equal to 2 times L plus 2E. F fundamental will therefore be equal to V over 2L plus 2E. V over. So let's look at the difference. If there's no N correction, the fundamental harmonic is this. If there is N correction, the fundamental harmonic will be this. Okay. And in open pipe, we know the harmonics to be a mixture of odd and even. So the second harmonic F2, which will be 2 times F1. So 2 times V on 2L plus 2E. 3 times, 4 times, blah, 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 blah. So this is what happens whenever there is a consideration for an N correction. Please, is there any question? Is there any question here? Because we want to move on to the resonance tube. All right. So as usual, I'll look for questions on this when there is a consideration for N correction as well for you, so you can try in order to master its application. Okay. So the resonance tube, as usual, the resonance tube, you also do this, okay, as an experiment in the lab. The resonance tube experiment. What is resonance tube? A resonance tube. In fact, the resonance tube experiment is an experiment that is used to determine the velocity of sound in air. The resonance tube, the resonance tube. The resonance tube experiment is an experiment. It's a laboratory experiment that is used to determine the velocity of sound in air. So the resonance tube experiment is an experiment that is used to determine the velocity of sound in air. That constant value of 3, sometimes 320 meter per second or 330 meter per second. Please let me take short of attendance, okay, and then get back to you, please. So the reason for which the value is not constant, okay, sometimes 320, sometimes 325 or 330. How is it done? So it is used to determine the velocity of sound in by using a tuning fork. A tuning fork with a fixed frequency. Now, the resonance tube setup is just like the burettes. We use the burette as you use in your titration experiment during chemistry. Then the burette is, we incorporate a tap to the end of the burette. So the whole setup is like this. This is the burette. The outlet of the burette. This is a tap. A tap just to control the water flow. Now, the resonance tube experiment work on the principle of closed pipes. It works, this works on the closed pipe or tube principle. So the burette is filled with water to a certain level. Now the water makes one end of the tube closed. So once this is filled with water, this end is closed, behaving like when you have a pipe or tube and one end is closed. Now all that in the experiment, all that we do is that we cause a vibrating tuning fork. Please, the tuning fork is similar to the fork you use at the dining hall. The only difference is that, you see, the fork you use, there are a lot of, it's like this. There are lots of prongs. But the tuning fork, we have only 2 prongs. And the tuning fork is used to generate this device we are calling as the tuning fork. It's used to generate waves. So if you want to generate wave with a particular known frequency, you use the tuning fork. Okay, so the tuning fork has fixed frequency. So when you pick it in the lab, its frequency is usually written on, maybe 212 hertz, blah, blah. So when you strike it to a rubber band and it vibrates, it produces a wave whose frequency is fixed. So we want to create a wave within a tube with a particular known frequency. Okay, so that's why we are saying that it is used, okay, by using a tuning fork with a fixed frequency, fixed or known frequency. So when the tuning fork is used to hit a rubber band, it sets the tuning fork into vibration. Then the vibrating tuning fork is brought closer to the open end of the burette. It's brought to the open end of the burette. When you bring it to the open end of the burette, you set the air column between the open end and the surface of the water into vibration. So the air column would vibrate. All that you want to achieve is that you want to achieve resonance, where the air column would vibrate to the natural frequency of the tuning fork. So when they respond, okay, when the frequency of vibration of the air responds to the frequency of vibration of the tuning fork. Let me give you this. When the frequency of vibration of the air column and air column, I mean this length of air. Okay, I said the water surface serves as the closed end, so this becomes the length of the air. That's what we mean by air column. When the frequency of vibration of the air column within the tube responds to the frequency of vibration of the tuning fork, resonance okay, since resonance in sound is characterized by the production of sound or loud sound loud sound will be heard on attaining resonance. This corresponds to the first resonance position or harmonic. So when the vibrating tuning fork is brought to the edge of the burette, okay, the air column within the tube is set into vibration. It will vibrate and then respond, adjust to the natural frequency of vibration of the tuning fork. And when that point is reached, okay, it would produce a loud sound. a loud sound will be heard. Okay, the production of the loud sound indicates that resonance position is attained. But the question is, how do we attain resonance? You obtain resonance by adjusting the water level. So the tube is initially filled to a certain level. Then as this vibrates, the tuning fork vibrates, you open the tap so that some volume of water will be overflow. As you adjust the volume of water, a certain point will be reached where resonance will be obtained. So resonance is obtained by adjusting the water level or adjusting the air column. Resonance is attained by adjusting the air column within the tube. So if I want to adjust the air column, length of the air column, it is just as a result of adjusting the water level. When the water level is coming down, I'm increasing the length of the air column. And a certain length, L, will cause the vibrating air within the column to respond to the frequency of vibration of the tuning fork. And at that point, resonance would happen. Please, is there any question? Is there any question?
No, please.
So all that I'm saying is that you don't obtain resonance by just keeping the vibrating tuning fork at the top of it. No, that will not happen. But you need to be opening the tap so that you adjust the length of the air column for resonance to take place. And when that point is reached, that loud sound will be produced. Now, the first sound, when that loud sound is produced, it corresponds to the first frequency, okay, or the first harmonic. So let's assume as the water level is adjusted, the loud sound was produced at a length L1. So L1 or L, that loud sound is heard. So when the loud sound is heard at this level L1, L here, the L here corresponds to the first notes, meaning the first notes is produced. This works on the principle of closed pipe. So the first note is produced. So if there is a consideration for end correction, which we mostly do under resonance tube, then quarter lambda is equal to that length of the air column L plus the end correction E. And lambda is equal to 4 times L plus E. Therefore, if we want to estimate or approximate the velocity of sound in air, we know that V is equal to F lambda. So V will therefore be equal to F times 4L plus E. 4FL plus E will be the approximate value. This is the approximate value of the velocity of sound in air. Don't forget, this F here is the fixed frequency of the tuning fork. So if the first loud sound is heard, which corresponds to the fundamental notes of close pipe, when you use this concept to determine V, it is termed as the approximate value of the velocity of sound in air. Why approximate? You understand why this is said to be the approximate value. Now, you can have more than one resonance positions, meaning that as you adjust the water level in adjusting the air column within the pipe, there can be more than one position where resonance will be heard. So if I heard loud sound at L1, then I strike the tuning fork to the rubber band and then bring it again and then continue adjusting the water level or air column within the pipe. Another possible length of the water column can produce another resonance. Let's assume that to be here. This is L2. This L2 also corresponds to the second resonant position or second possible stationary wave, whose notes under closed pipe is like this. So the second position of resonance corresponds to when you have a closed pipe and then the second possible stationary wave, which is formed. Okay, so the second loud sound heard also corresponds to the second resonance, which is this. Now, if there is an end correction, you realize that. So in this case, please, it can be by considering end correction or without end correction. Take notes. Okay. So if there is consideration for an end correction, the approximate value will be this. If there's no consideration for end correction, then L will just be equal to quarter lambda. This will not be there. And therefore lambda will be equal to 4L. For velocity of sound to be equal to F times 4F times L. Take note. So there can be a consideration for end correction. There can be no consideration for end correction. In practicals, usually we don't consider end correction. So if there is no end correction, then lambda, the length of the tube, will be equal to 1, 2, 3. So 3 times quarter lambda. And this is L2. Earlier, L1 is this. L1, when the first resonance position is equal to quarter lambda. Okay. L2, therefore, will be equal to 3/4 lambda. And L1 is half lambda. Now, because we have two resonance positions, we want to consider the first resonance position, consider the second resonance position. Okay. So let's, in this equation, this is equation 1, equation 2. We are considering both resonance positions. And 3 lambda in equation 2, 3 lambda will be equal to 4 times L2. In equation 1, lambda will be equal to 4 times L1. Let's subtract this equation from this. 3 lambda minus lambda is equal to 4L2 minus 4L1. Therefore, we have 2 lambda giving us 4 out L2 minus L1. This is equal to 2L2, 2 into bracket L2 minus L1. So the velocity of sound in air V, which is equal to F times lambda, is equal to F times 2L2 minus L1. 2F L2 minus L1. This value of V is termed as the exact okay value of the velocity of sound in air. It is exact because over here we are considering more than one position of resonance. So it is termed as exact or accurate because of the consideration of 2 positions of resonance. So if you want to be exact in your value of velocity of sound in air, then consider the first, then the second positions of resonance. And your value of V would be accurate or correct or exact compared to considering only one. That is why when you consider the first value, first resonance to determine V, we are terming that as the approximate value. Okay. And when you consider the second position of resonance to determine V, it is more accurate or exact. Because over here, you see, in practicals, the reason why we take 2 readings and then later determine the average is that by considering 2 readings and finding the average, it minimizes the errors involved here. So this is the reason why when you consider 1, 2 resonance positions to calculate for the velocity of sound in air, the first one is termed as the approximate, and then the second one is considered to be exact or correct because it minimizes error. Please, is there any question?
No, please, can you move the camera down?
I have a WASSCE 2022 question on what we are doing. I want us to quickly apply that. Okay, apply it to solve the question.
Stage, yeah.
Hello, Amma.
Please, you didn't finish your sentence. You wrote exact value of.
the velocity of sound in air.
Okay.
The exact or accurate. So it's accurate because of our double consideration of the first resonant position and the second resonance position. Considering just the first is an approximate way of determining the velocity of sound in air. Usually you can possibly have two. You can possibly have two because if even if there is a third one, the third one usually is so faint, the sound head. So that is the first, and then the second, that is mostly considered for estimating the velocity of sound in air. Please, can I go ahead? I'm reading. In a resonance tube experiment, in a resonance tube experiment to determine the speed of sound in air, a tuning fork of frequency 240 hertz, a tuning fork of frequency 240 hertz is sounded above the end of the tube. Is sounded above the end of the tube. If the first and second resonance, if the first and second resonating length are 0.34 meter, 0.34 meter and 1.05 meter respectively, if the first and second resonating lengths are 0.34 meter and 1.05 meter respectively, calculate the I. Calculate I. Calculate I, the approximate speed of sound in air. Calculate I, the approximate speed of sound in air. Then II, the accurate speed of sound in air. II, the accurate speed of sound in air. So in a resonance tube experiment to determine the speed of sound in air, a tuning fork of frequency 240 Hz is sounded above the end of the tube. If the first and second resonating lengths are 0.34 and 1.05 meter respectively, calculate I, the approximate speed of sound in air, and II, the accurate speed of sound in air. So give it a try. Give it a try within 5 minutes. Okay, let's go through. So the approximate value would always correspond to the first resonant position. So if the first resonant position is at maybe L1, over here we are told that the frequency of vibration of the tuning fork is 240 Hz. Well, F is 240. So L is equal to quarter lambda. Here, we are not given any value for N correction. So we won't consider N correction. Therefore, lambda is equal to 4L. V therefore will be equal to F times 4L, which is 4 times FL. So once the frequency is 240 times the first resonance position is 0.34. What will be the velocity of sound in air? What will be V? Class, what will be V? The value of V. Good. So this is 326.4 meter per second. And there's the approximate value. Approximate value. Now, assuming a second resonant position is obtained at then this time around we'll have L being equal to 3/4 lambda and 3 lambda will be equal to 4L2. This is L2, this is L1. So as the relation as we obtain 3 lambda on lambda will be equal to 4L2 minus L1. Therefore, lambda will be equal to 2L2 minus L1. And if this is it, then V is equal to 2F L2 minus L1. 2 times 240 times 1.05 minus 0.34. And this time around, 480, then the difference. F this time around is equal to, what's the value of V this time around?
040.8 meters per second.
So approximately 340.8 or approximately 341. So this becomes the accurate, whereas the first one becomes the approximate value. That's all. That's simple. Any question? No question. Okay, I I earlier was telling you about the fact that velocity of sound longitudinal wave in air depends on factors. Velocity of sound in air, here not sound, but longitudinal wave, because a sound wave is a longitudinal wave, depends on temperature by this equation. So V is directly proportional to T. By this equation, what it means is that when temperature increases, the speed of sound in air must also increase. So it means that in the day, when you speak, it must travel faster than in the night. But Charlotte, is that what happens? Charlotte? Or
Yes, dear.
by this equation, it means that when you speak in the day, temperature is higher than in the evening. So when you speak during the day, it must travel faster than in the night. But is that what happens?
Yes.
Are you sure?
Yeah, I don't know.
Yes.
Compare during speaking in the night and then in the day. Which one travels faster?
Say it's in the night.
But this is not actually so. Velocity of longitudinal wave depends on temperature. It's directly proportional, meaning that in the day when temperature of the environment is higher, sound must travel faster than in the evening. Okay. It doesn't look like that because in the day, there are a lot of factors that create sound. Okay. So cars are moving, noise are being made all around. So it interferes with the sound produced. That is why it doesn't travel as it's supposed to be because of the factors. Okay. So it means that if you consider two different temperatures, temperature at 0K and temperature at T, okay, or a temperature at 0 degrees Celsius and T degrees Celsius. We have V at 0 being directly proportional to T at 0. T at 0. Then V at T must also be directly proportional to temperature at T in degrees Celsius. V at T on V at O must be equal to square root of T at and then T at 0 when we take ratio of these two. Now, these are temperatures in degrees Celsius. I want us to look at how temperature relates to velocity of sound in air. So let's change these temperatures in degrees Celsius to Kelvin. So VT over V at 0 will be equal to This is 273 plus T over 273. Now therefore, TK is equal to 273 plus TC. So if there's the equation that is used to convert temperature in Kelvin to degrees Celsius. So if I have a temperature of 0 degrees Celsius, I want to convert it to Kelvin. This is TC 0. That's why I'm left with this. And then if I have temperature small t in degrees Celsius and I want to convert it to Kelvin, it is 273 plus that temperature. So that's why I have 273 plus T. Please, is it understood? Hello?
Yes, please.
So, we have 1 plus T on 273 raised to the power half. I'm dividing through by this. 273 divided by this and T divided by that. And then the square root sign is what is changed to have. Okay. VT on VO is equal to, if you expand this and consider the first two terms, okay, the first two terms would give you a larger value, okay, the other values are small. The reason why we only expand this to the first two terms, 1 plus half T on 273. We are only considering up to the first two terms because that will give us larger values. You are EMA students, so you should understand. 1 plus multiply 273 by 2 and then divided by 1 for me. Amma,
Yeah, please, I still don't get that part. Why
No.
you have multiplied.
in binomial expansion, as you expand, the first two terms will give you a larger value. Subsequent terms will be smaller. Okay, so that is why we are only leaving this to the first two terms and not third, fourth, and all this. Are you okay?
Yes.
So multiply this by this for me and then divide 1 by your results. Please, I'ma do that for me quickly. We have 8 minutes to go. 273. Amma, you are not done.
Yeah, please, I got 546.
I said divide your answer by 1.
Yes, I got 546.
No, you won't get that. Give it to me in decimal. You won't get that. You'll get 0.00183. Yes, this will give you 5 something something. But when you divide 1 by 5 something, you get this. Are you okay?
Yes, please.
Now, VT is equal to V naught times 1 plus 0.00183 T. What is velocity of sound at 0K is approximately taken as 320. Sometimes it's taken as 330. So depending on whatever you are given, if there's then 320 times 1 plus 0.00183 T. Let's expand 320. Multiply 320 by this. 320 by the coefficient of T. Are you people there?
Yes, please. You get 0.5856.
So approximately 0.6 0.6 T. This is the equation connecting temperature to velocity of sound in air. What this means is that at every 1 degree Celsius rise in temperature, velocity of sound in air, velocity of sound in air increases by 0.6. So velocity of sound at zero Kelvin is considered to be this constant. Okay, meaning that if this temperature must increase by 1, okay, you have this plus 0.6. So at 1 degree Celsius rise in temperature, this constant value would increase by 0.6. At 2 degrees Celsius rise in temperature or change in temperature, you have 0.6 times 2 added to this constant value. So at every 1 degree Celsius change, not rise, but change in temperature, velocity of sound in air increases by 0.6. Amma, your hand is up.
Sir, please, that 320, is it a fixed value or we assume that?
It's a constant value, but usually it is given as, if you look at the books, it is either 320 or 330. So it depends on whichever is given. Okay.
Okay.
So velocity of sound at 0 K can be this or this. So whenever there is any 1 degree change, this factor being 320 or 330 would also change by. So at every 1 degree Celsius change in temperature, velocity of sound in air increases by this amount. That is why we say that velocity of sound in air depends on temperature. It's not fixed. When temperature is increasing, it is always changing by a factor of this. Please, is it understood?
Yes, please.
Okay. All right. So that is it. Now, velocity of sound in air is also related to density of the air by this equation. V is inversely proportional to square root of density. Temperature directly proportional to density is this. And so if density is increasing, then V is decreasing. If density is decreasing, this is increasing. An increase in this, a decrease in that. A decrease in this, an increase in this. Let's connect that to temperature. You see, we can connect density to temperature. As temperature increases, what happens to density? Chemistry and physics students, as temperature increases, what happens to density? Hey, Adwa, as temperature increases, what happens to density?
Decrease.
It decreases.
Please, can you come again?
And I shall come again, say, oh, me and my voice, I come again, say,
Oh, I'm sorry. My siblings were making my.
oh, assembly. Like, the question is that as temperature increases, what happens to density? When temperature increases, density decreases because temperature will increase the kinetic energy of the molecules. And when the kinetic energy increases, they will space out the more. So as temperature increases, density decreases. So if density is decreasing here, then velocity of sound must increase. So this also connects velocity to temperature. Temperature, increase in temperature decreases density. And so, yes. So that's the relationship with temperature has with velocity of sound in air, and density also has with velocity of sound in air. Is there any question? If no question, then Merry Christmas to each one of you. Ama.
This question is related to velocity and temperature. So if they give you a question which ask for, so please can I see the question?
Okay.
Yeah. So the question goes like this: sound travels with 260 meter per second in air at 24 degrees Celsius. How many times must the temperature in terms of degrees Celsius be increased so that velocity changes to 340 meter per second? So if
Just,
they give you a question,
just use this because it's about velocity and temperature.
yes, please.
Mm. All right. So Merry Christmas to all of you, and then a happy and a prosperous New Year. But please be very careful.
Some of us don't celebrate Christmas.
I'll come to those of you. But in fact, be very, very careful as you move around. Okay. Yes, this is a season where people because of over anxiety and happiness, they can also drive around, okay, in that disorderly manner. So please, as you move around, as you go step out to attend to parties and other stuffs, be very, very careful so that we can all gather or meet after Xmas and then continue our good work. Don't forget, WASI is our target because we want to do medicine, pharmacy, engineering, and all that. Okay, so let's be very careful. Those of us who do not celebrate Christmas, happy non-celebrating Christmas. And you also would have to take very good care of yourself, okay? Because whether we celebrate or
Yes,
we
please.
must be here after Xmas and after New Year. Okay, bye-bye. If you have any further question or problem to help, and do not relent in your solving of problems. Okay. We'll meet after Xmas. Take good care of yourselves and bye-bye.
Bye.
Ah.
Those of you who do not celebrate Christmas, bye-bye.
Bye.